Let's go over 2005 question 3 Form B test. It's a nice rate law question that incorporates their integrated formulas for rate law. Okay, so we've got a reaction, x by itself, going to 2y plus z. All right, so the decomposition of gas X produces gases Y and Z is represented by the equation above. In a certain experiment, I guess this one, the reaction took place in a 5-liter flask at a certain temperature. Here's the data from the experiment. Now, this is a rate law question. Now, you may or may not recognize it. One way to recognize it is a natural log of the reactant. Okay, and then of course x to the negative 1 is the same thing as 1 over x. Okay, so if you notice, they're kind of implying possibly some values um, of our initial concentrations. And of course, you have x, and you notice it's going down. So you kind of have the rate of decrease of x as it goes forward. And here's some time. And time is the big factor in terms of identifying as a rate law. Now also, they graphed, it looks like they graphed the change of the concentration of the reactant over time, and then the ln of x, and then the 1 over x. Remember, that's the same thing. And that should be screaming to you. This is remember, there's many ways to identify the orders of a reaction. The first one, of course, is eyeballing some data if you have an experiment where rate is given to you and the initial concentrations. This is not that kind of question. You can't eyeball anything here. Here you can look and see that the x is decreasing over time, and then they have some ln of x and x to the negative 1 values. And so the second way that we can identify the order of a reaction is through a mechanism. That's not given as well. So now we're on the third way, and that's identified by using our integrated rate law equations and looking at the graphs given. So just because it's here, and I see something here, I see the ln of x when it's y, and I see over time, in this case we're using minutes, I see a straight line. And this is negative k right here. This screams to me that this is first order. How do I know? Well, I know that the natural log of the concentration of x over some time period, okay, minus the natural log of x to some initial concentration is equal to negative kt. This is given to me in my reference table. And by the way, in the reference table, they also give you 1 over x to some time period minus 1 over x 0, and it's equal to positive kt. Now, they list these equations right in order. So guess what, party person? This is the first order, this is the second. Now, what you should recognize is that if I was to move and rewrite this equation for the first one and have ln of x over t, okay, equal negative kt, and remember this is going to be positive now, positive ln natural log of x to the 0 power. What I have here is I have my y equals mx plus b. And so I have my slope is k. And notice there's a negative sign here. And of course, we got this from integrating, okay, the rate law for the first order. And so this is screaming rate law. So r is equal to k, okay, x to the 1, because we get a straight line. This is a linear equation. If you get a straight line, okay, from plotting the x using the integrated rate law formula, in this case, this worked out the best. Notice the 1 over x, you could do the same thing. You could, again, if I went to 1 over x, that would be 1 over x to the some time period, which is my y, equals kt. Notice it's positive in that derivation, okay, plus 1 over x to the 0, and we still get our y equals mx, except this time we notice the slope is positive, but we should get a straight line if it's second order, but we don't here. So it screams first order because of the linear line that we get when we plot ln of x as the y, okay? And of course, if it was 0 order, it'd be a straight line, and that's what you get when r equals x to the 0 order, okay? So clearly we got a winner here. But that's only one of the questions. In fact, one of the questions states, okay, what is the order of respect to x? And you would say 1. Justify your answer, and you would say the plot of what? The change of the ln, natural log of x versus time is linear. And that's all you need to say. Okay, but let's go back to question A. How many moles of X were initially in the flask? Okay, so now we're getting a little stoichiometry. So again, this is a different kind of question. This is not an experiment in terms of seeing how the initial concentrations change. All they're showing you is over time period how the values of X are going down. Okay, so in the initial time 0, we have 0.00633. Okay, so let's do that math down here, 0.00633. And this, of course, is a concentration. It's a molarity. Now, they must have told me, since I'm after moles, what the volume was. Okay, I see I'm missing a 0, but I can fix that. So it's in 5 liters. So 0.00633. My short-term memory is gone at this height. So I've missed a 0 here. Okay, that's my molarity. Now I'm going to times that by my volume, which is 5 liters. And that's always going to give me moles. Okay, liters times molarity, if you've been through this. Okay, I shouldn't have to make that any sense. So 0.00633 times 5. And so I get the amount of moles is 0.03165 moles. Careful, I have 3 sig figs here. I want to show 3, so 0.0317 mole. Okay, notice the liters given to you, just to be careful, is also 3 sig figs. Remember, ending zeros count when the decimals are present, so that's 3 sig figs. So party person, that's 5.00. Any case, 0.0317 moles. And that's pretty straightforward. That was just a molarity times what? Volume question. And that's giving you a point there. And I get, of course, 0.03, and again, I'm so bad with my memory here, 17 moles, maintaining 3 sig figs. And that's all she wrote there. So let's go on to B. How many molecules of Y? Ooh, they're asking for the actual number. So when I hear molecules, I think, ooh, take my moles and convert them to the actual number using Avogadro's number. Been a while, but we can do this. We're produced in the first 20 minutes. So we want to know how much Y is produced. Now, if you notice, people, we don't have a value for how much Y, which is one of the reactants. But we know something about stoichiometry. Okay, we do know that there's 2y for every 1x. So if we think about this, the missing x becomes y. And if you know anything about the equilibrium problems, if we're going to minus x here, this will be plus 2x. So let's figure out how much minus x we have. Remember, it's from 0 to, I believe, 10 seconds. Okay, or is it 20? Let's go look again. I know you're screaming at me, making this longer. Okay, but first 20 minutes, I can do this. Okay, so we're going to go from 0 to 20. All right, so I know I'm going to find the moles, okay, at 20. So same thing, 0.00427. That's the molarity. I'm going to times that by my 5 liters. That's to give me moles here. So take my handy dandy calculator, 0.00427, and I'm timesing that by 5. And so the moles I get at 20, okay, is 0.02135. Care about the sig figs right now. Now, that's great, but remember I didn't start from 0 here, right? So that I'm looking for the change in, I'm looking for how many moles have changed, so I have to figure out how many moles here. So we already did that number, right? We already found the moles at time 0, and that was 0.0317. So 0.0317, and this is the moles I started with, and this is the moles I have after 20 minutes. Okay, I'm going to subtract these two, and that's going to give me the total loss of moles. And once I have that, I know what my minus x is, right? 0.0317 minus 0.02135. And so I get, party people, I get 0.035 moles. Okay, now that's moles of what? X. Now, what were they asking for? They were asking for how much mole of Y was produced. Well, if I have 0.034 moles, and I had to subtract these two to know how much the moles decreased, I know my minus X is that. Well, therefore, it's 2 times that. I mean, if you want to get fancy, okay, we have mole of X, and then we know what? Well, there's every 1 mole of X, there's 2 what? 2Y if you want to get all fancy. But you're timesing it by 2, so let's do that. Times that by 2, and you get 0.0207. I'm going to try to maintain 3 sig figs, so I'm going to get 0.021 moles. Now, careful, 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 okay, because we found the total moles of Y. What was the question asking for? They're asking for the molecules of Y. So I'm going to take my 0.021, and that's moles of Y that I got through stoichiometry, through the ratios. If you're noticing, we're always having one of those little type of ratio questions in every one of our problems, okay? And what do I know, party people? I know that if I want to get rid of moles, moles goes on the bottom. Every mole is equal to 6.02 times 10 to the 23, and that's molecules, as I read it like that. So take that, and I'm going to times that by 6.02, second function e to the 23, and what I get is approximately, keeping 3 sig figs, 1.25 times 10 to the 22 molecules. Now, of course, it probably be atoms, but hey, molecules of Y. So a little bit of a stoich here. We had to figure out total moles, okay? We had to figure out total moles from the 0 position to the 20, okay? So we found the moles of both, had to subtract, okay? And then, of course, do our stoichiometry to get Y and then convert to molecules. So a few steps there, but nothing too difficult. A nice little cute little problem there for sure. Okay, so what's the order with respect to X? Well, based upon the plot, it's first order, okay, because of what we talked about previously. Write the rate laws, okay? R is equal to K of X to the first order because of the plotting of ln of X versus time is linear. Okay, next little piece. Let's calculate the specific rate constant for this reaction. So I would love to use R equals K, and a lot of people did not know what to do with this. And this would be nice, but I would need a what? A rate, okay, to solve for X. And I would need a what? An initial concentration, which we do have, okay? But that's not going to work. We don't have a rate. So party people, we're going to have to use our integrated formula. Okay, woo. Okay, so what's our integrated formula? Okay, well, it's going to be the natural log of X after some time period minus the natural log of X initially equals negative KT. So we're forced to use our integrated rate law equation. We can do this, okay? So if you notice, after some time period, it won't matter what value we use because K is going to be constant. So let's go pick a couple of values. So let's go pick after 20. Let's be consistent. So let's do after 20. 20 minutes, 0.00427, 0.00427. So that's 0.00427. It's a molarity. That's my X of some time period. And what was the initial? That's this little 0 is initial. Okay, what was that molarity? And that was 0.00633. That's minus the natural log of that concentration equals negative K, which we're after, time period, okay, of course, is going to be 20 minutes. And now we solve for K. Now, if you're not comfortable with these values, you could actually just take the natural log of these and minus, but also you should recognize the fact that when you're minusing exponents, you're dividing. I mean, I don't know what works best for you, but this is how I see it. The natural log of this, what, 0.00633, okay, equals negative k, which is 20. So I'm going to go find this. Let's take 0.00427 and divide by 0.00633. Okay, that gives me the natural log of 0.674. Let's just keep it 6. Solve for k, right? So that's going to be negative 20. And since this number is less than 1, it's like, it's a logarithm, so it's going to be a negative number, and this negative number is, the negative makes a positive value. But hey, let's take the natural log of 0.6746. I can do this with our handy dandy calculator. And if people want to know what that is, make sure I'm correct. So the natural log of this is negative 0.3937 all over negative 20. So as I said, these will be positive, positive. Divide that by negative 20. And what you get is your k is equal to 0.0197. I'm going to maintain 3 sig figs throughout the process. Now this is 20 that says 1, but I bet the 20 minutes had at least 3 sig figs. Actually, 20 minutes actually have just 2. Okay, so the least significant number would be 2. If you put 3, I think you're okay, because it's usually plus or minus 1 off. So 0.020 minutes. Oh, actually, I'll have to figure out the units in a second. Okay, so that's the numerical value, all right, which we should have no problem getting. Now, the next thing I'm going to do here is get my units. Now, I could work through the units here, or I can realize that if I did R equals what? K to the X to the 1, well, I know this is molarity. Rate's usually what? Molarity per second. Now, this is molarity per minute over solve for X. This is just molarity. You can see it's just 1 over minute. So this would be minute to the negative 1. Okay, and you get a point for this and a point for that. Now I do see the key showing 0.0197 as the answer, carrying 3 significant figures. But I do believe that this would be the better answer, but they'll take plus or minus 1 significant figure. Could you have figured the K differently? Sure. Notice this is the same unit over the same unit, which is molarity here. Okay. Actually, the molarity over molarity would cancel. Okay, and then you're left with what? Minutes here. So the molarity here. Okay. Well, so if we did the molarity here, remember this is a molar and this is molar, they would cancel, and you're left over a minute, and there you go. So very interesting to understand that this is 1 point always for the numerical answer and 1 for the unit. Min to the negative 1 is 1 over min. Okay, so last little piece. Okay, and I'm going to make some room here. So hold on to your party hats as this may flash on you. Oh, my RAM's pretty good. Oh, a little bit of flashing. Okay, now let's go there. So now the last question, which is the one I really care about most of all, the rest of that was pretty fun, was F. Calculate the concentration of X in the flask after 150 minutes of the reaction. All right, well, great. All we got to do is what? Just go and 150 what? Minutes. Oh boy, it stops at 100. But I do know my initial. And because they're asking how much should be left after a certain time period, and I know because of the graphing here that I'm dealing with what? First order integrated equation that's dealt with how much time. So they're giving me the time. They want to know how much is left after some time period given the initial. And that's where we need to understand, that's where we need this formula. They're asking for a given amount of time, 150 minutes, how much after some time period, 150 minutes, given the initial concentration, would I have left? Of course, it depends upon our rate constant, which we all know is based upon activation energy and temperature, okay? So, or fraction of molecules that can collide and be effective. So let's put that in, make sure we know our initial is 0.00633. Okay, so let's just go write this, the natural log of x some time period minus the natural log of x of 0 equals negative kt. That's given to us. Okay, so after some time period, again, thereafter, how much is left? What's the cat in the flask after? So we're solving for this x. So what do we know? Ln of x, some time period. We know the initial, 0.00633, I think, just to make sure. 0.00633. Should trust myself. I know my K now, so I can put that in. I found my K to be 0.0197, right? We found that right over here, right? 0.0197, 0.0197. And we know that it's a negative value, and the time is 150 minutes. All right, so let's go find this number here. So remember that negative kt there. So I've got 0.0197, 0.0197 times 150, and of course big finger errors, negative 0.0197 times 150, and I get negative 2.955. Okay, now I'm going to take this and go plus the ln of 0.00633, and this will be plus the natural log of 0.00633. Let's go find that number. The natural log of 0.00633, and what you get is you get this number to be a negative 5.062. Okay, so if we take this here, add these two together, plus negative 2.955, and what we get is a negative 8017. Okay, and now we have the ln of x for some time period, which of course is 150 minutes. Okay, that's what we're solving. And so to do this, what we do is e to the x to both sides. And why do I do that? Well, e to the x brings this down to x, and this becomes e to the negative 8.017. So let's do that. Second function, e. And what I get is my ln of x, or I should say, sorry, the concentration of x at 150 minutes is equal to 3.2. So I get 3.296, which times 10 to the negative 4. And of course, that's going to be what? How much? That's the molarity after 150 minutes. Now, of course, I should get rid of, make sure my sig figs, keeping 3 point, this should be, this 6 is greater than 5, so 30 times 10 to the negative 4 molar. Make sure you use your units. Okay, so in any case, there is your answer there in all of this mess. Hopefully that helped. Okay, not too difficult, but if you're not used to using, your natural logarithms, okay, be careful. Also, a pitfall here, if you were to do ln of x over t over the ln of x over 0 and then solve for that, you may want to, or you could have incorrectly did the ln of this number, which would be here, and then times it over, and that wouldn't work out because really what this is natural logs here. Any case, hope that helped.